Hi all, welcome to lab number 6 of GG497, Geological Visualization. In this lab we'll be looking at folds and fold geometries and how we can understand what folds look like using structural contours. The lab will be in two parts. The first part, using questions 1 to 4, relate to map 6A, which is on the following page. And on map 6A, hopefully you can see that there's this symmetry, this repeating pattern to the rocks, which is indicative of folds. For instance, in the southern half of the area, you can see that we go from brown to purple to yellow, back into purple, back into brown. That sort of repetition is very characteristic of folds. And in the north of the area, we've got a similar repetition involving some of the same rocks that goes from purple to brown to green to brown to purple. And I bet if we could continue our map in this direction, we'd end up back into our yellow unit. The second half of the lab refers to this map, map 6B, which shows a similar sort of thing where we have this repetition of different rock layers. But the difference between this fold and the previous one is that this fold has a plunge to it, and that is where the fold hinge, the axis, is inclined. And we'll see how structural contours appear for both situations, where we have upright folds and plunging folds. Okay, so the first question asks you to mark on the fold axial traces present in the map area using appropriate symbols, and gives us a hint that drawing structural contours for the limbs will help. Okay, well, if we've got folded rocks, then we have these two limbs. We have the upgoing limb and then the downgoing limb. And what we should try to do is find a contact present on one of those limbs that we can follow all the way around the fold. So why don't we have a little look for a contact where we can find the heights of it in multiple places. And I quite like the look of, if we're looking at this fold in the southern part of the area first, I like the contact between the yellow unit and the purple. So I'm going to go ahead and mark all of the points where I know the height of that contact, in other words, where that contact hits the topographic contours. Then what I can do, in similar way to how we've done for all of the other labs so far, is I can join the points of equal height with a structural contour, and that shows me where that contact would be anywhere on the fold. Anywhere along this line, the height of that contact is going to be 300 meters above sea level. Anywhere along this line, that contact between the yellow and purple unit will be 260, and so on. Then what I can do is find another contact for another part of the fold. Why don't we have a look at this one of these folds where we've gone from a repetition of brown to purple to yellow, back into purple, back into brown, green, and then back into brown, and then back into purple. So it looks like we've got another hinge zone or core of a fold in here. So why don't we drop on some structural contours just like we did for our contact between the yellow and purple, this time using the contact between the brown and the green. So I mark on all of the points where I know the height of that green on brown contact, and I draw me some structural contours. Now the fold axes in this situation mark where the structural contours reach a point of inflection, so where they curve from one limb into the other limb. And if we look at our southern fold first, you can see that the height of the contact between the purple and yellow is at 300 meters along this line. Then it goes down to 260 meters. Then it's at 260 meters again, and then it goes back up to 300 meters. So we can assume that as we go from here in this direction, we're going down, 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 then we start going up, 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 up. So the point of inflection for our fold hinge in the southern half of our area is between the 260s structural contours. Similarly, for the fold in the north of the area, we're at 220 here and 260, so we can imagine we're going up, 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 and then we get to here, and then start going down, 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 down. So the point of inflection is going to be parallel to the structural contours between the 260s. So we can mark on the axes of the axial traces of the fold, where the fold axis would be on the surface. Then what we can do is add in the appropriate symbols to show which is a synform and which is an antiform. And if we look at this one highlighted in red, we can see that we start at 300 and then we go down to 260 and then come up back to 300 the other way. So this one, highlighted in our red structural contours, would be a synform because we go down one limb and then up the other side. Whereas the fold that's highlighted by the blue structural contours, we start at 200 here, we go upwards to 260 towards the fold hinge, and then once we cross the fold hinge we start going down again. So this is an antiform. So we can use those different symbols. A synform, the arrowheads are pointing together, and an antiform, the arrowheads are pointing away from each other, and that allows us to distinguish different types of fold axial trace on a map. Okay, the next question asks us to calculate the interlim angle for the folded rocks immediately underlying Wisp Fell. So Wisp Fell is this mountain top here, and we want to know the interlim angle of the fold. Okay, well the first thing that we need to do is find out what the map scale is. And our scale, when we put our ruler against it in your lab book, we see that 23 millimeters on the map equals 20 meters in real life. It's another one of these strange scales that's somehow been photocopied awkwardly. But in any case, the scale still works. It's still a scale, and it tells us that 1 millimeter on the map is equal to 0.87 meters in real life. Then what we need to do is calculate the dip of one of the limbs, and we can do this using trigonometry if we know 2 points on the plane where we know the height of that plane. So 2 points on different structural contours that are perpendicular from each other. So here we know that the plane, or would be the plane between the yellow and purple bed, would be at 300 meters height, and here it would be at 260. Then what we do is measure the horizontal distance between which that change in height occurs. So the distance between the 2 points on the map is 18 millimeters. If we multiply that 18 millimeters by the map scale, it tells us that that horizontal distance is 16 meters in real life. So now we can draw one of our triangles which captures that geometry. We've got a height change of 40 meters from 300 to 260. That occurs over a horizontal distance of 16 meters. So the dip of our bedding plane in this part of our map, if we apply trigonometry, we take the inverse tangent of the opposite over the adjacent, so in our case the inverse tangent of 40 divided by 60 gives us a dip of that limb of 68 degrees. Now we could repeat that again and again, but we can see that our structural contours across all of these folded rocks, they're equally spaced and they're parallel. So in other words, they have the same gradient and the same direction. So all of these limbs have a dip of 68 degrees. This limb here that we just worked it out for is dipping into Wisp Fell, and this limb here is dipping towards in the opposite direction. Okay, so all of our limbs of our folds have this dip of 68 degrees, and we can tell that by the fact that the structural contours for the limbs, they're equally spaced and they're all parallel. Okay, so then if we need to calculate the interlimb angle of the folded rocks immediately beneath wisp fell, then we can simply draw a schematic triangle showing that our beds are dipping at 68 degrees on both limbs as they head towards the hinge. So the interlimb angle for the fold beneath wisp fell must be 180, all of the degrees in a triangle, minus those two limbs to give us the interlimb angle of 44 degrees. Okay, the next question asks us to construct a cross-section along the section line XY to show the topography and position of the strata at depth. So another little schematic cross-section that shows the hill profile and the dips of our beds in the subsurface. So to start this, we'd place our strip of paper across the section line between the bounding marks between X and Y, and mark on the ground height of the contours that we cross along that section line. So luckily our hill profile is relatively simple. We go from 260 there, 300, and that's about it. Then we can mark on the rocks that we would find at the surface by adding a thin veneer of colour along the strip of our cross section to show what rocks would be cropping out the surface at those locations. And then what we can do, because we're going to draw this using structural contours, we're going to mark on the structural contacts between the yellow and purple layers and the green and brown layers. So these red structural contours, these ones here, they're marking the contact between the purple and the yellow. And these ones, these blue ones, are marking the contact between the green and brown unit. So wherever we cross those, we mark them on our strip of paper. Okay, at this point we've got all of the information that we can get from this map and everything that we need to draw our cross section. So what we can then do is transfer the information from our cross-section strip, starting with the contour heights of the ground from the cross-section strip and putting them on the cross-section panel. So these black marks that show the height of the ground, I place those on the cross-section panel at the appropriate height, and then I join these points to show the hill profile for the cross section, what I estimate the hill profile to be. I don't cross any of the other cardinal contour heights, and I interpret where the hills are and where the base of the valleys is, where they'll be on our hill profile. Next, I want to transfer the rock types to their position on the surface of the hill profile. So I draw marks directly upwards from the cross-section strip I've drawn to where they intersect my newly drawn hill profile, and then I can add in a thin veneer of colour to show where the rock types on the surface would be. If I can't do anything in the subsurface yet, at least I can show where those rocks are going to be on the top of the hill. Okay, then what I can do is transfer the structural contours from the cross-section strip to the appropriate heights on the cross-section. So just like we did in lab number 4, where we had the contact between the breccia and the mudstone, what we're going to do is mark on the heights of these contacts at the appropriate height on our cross-section panel using the information we've gathered from our structural contours. So all of the ones in red are the contact between the yellow and the purple unit, and all of the ones in blue are the contact between the brown and the green. Then what I can do is link these points to show how the surfaces have been folded. So I can do the brown and the green goes like this, and then I can do the yellow and the purple goes like this. And then I can interpret the other contact. So for instance, the contact between the purple and the brown, I know that all of these rocks are conformable. I can tell that from the map and the structural contours. And if you think about it, if this contact between the yellow and the purple is parallel to this contact between the green and the brown, then the contact between them is probably going to be parallel to those two as well. In fact, it has to be. So I interpret the run of the other contacts. And then what I can do is add color to show the geology in the subsurface. So I've got it I've got this thin veneer which tells me what the rock types are on the surface, and then I can just continue those colors up until the contacts with the other rocks. Now the last question for this part of the lab asks you to give a full description of the characters of the folds in the area. So basically, like, describe the geometry. Well, what I can say is that they look chevron in shape. They look pointy. They're not cylindrical, you know, nice gentle curve. They're chevron. They are symmetrical. You can put a plane straight through that and get a mirror image either side. They're horizontal, and that means that they're not plunging. Their fold hinge is perfectly horizontal, it's perfectly flat. And these are tight folds because their interlim angle is 44 degrees, which is between 10 and 60, which is the definition we use for tight folding, as opposed to open folding or isoclinal folding. Tight folding is where you have an interlim angle of between 10 and 60 degrees. Okay, that's the first half of our lab. The second half of our lab asks you to mark the fold axial trace present in the map area using appropriate symbols. And again, a hint for this is to draw structural contours for the limbs. Okay, well, we can see that these rocks must be folded because we've got this mirror image repetition of the beds. We go from blue to red to yellow to red to blue. So it looks like these are folded. And figure out the orientation of that fold, we can draw structural contours. So why don't we find a surface where we can find the height in multiple places? I quite like the look of the contact between the blue and the red, between the marl and the shale. So why don't I mark on all of the places that I know the height of that contact? Everywhere that it crosses a ground contour, I'm going to mark. Okay, now one of the problems that we've got here is that if we were to connect these points, we're going to have to bend our structural contours. In all of the examples we've seen so far, we've been able to draw a straight line across the map area that's connected all of the points without any deviation. However, in order to join these points to make our structural contours have to bend. They have to, in other words, fold, which is kind of what we'd expect since we're dealing with folded rocks. Okay, so these structural contours show the dip of that contact between the blue and the red unit in different parts of the fold. So you can probably guess where that hinge line is going to be. But if we first of all try and figure out what sort of fold it is, let's have a look at what we might say for the direction of dip. In this part of the fold, we can see that we're starting at 250 meters here, and as we go in this direction perpendicular to the structural contours, we're going down dip. So these rocks in this part of the fold are dipping in this direction. Whereas in this part of the fold, we can see that we're starting high here and going downhill in this direction. So the layer in this region of the fold is dipping in that direction. So I've denoted those using our dip symbol. And that point of inflection in the structural contours defines the fold hinge. That's our point of inflection, where one limb of the fold has a uniform dip and then it bends to be the other limb with a different direction of dip. And you can see that those dip symbols for the limbs, they're converging, they're dipping towards each other. So we use a synform symbol to show that the two limbs are dipping into each other. Okay, the next question then asks us to calculate the interlim angle of the folded rocks. And again, just like in the previous example, we need to know the length of the map scale first. And our map says that that 33 millimeters on the map is equal to 50 meters in real life. Therefore, 1 millimeter on the map is equal to 1.5 meters in real life. Then what we can do is use 2 points where we know the height of the contact and use simple trigonometry to work out the angle of dip. So these 2 points, I know that the height of the contact is at 250 here and 150 here. So there's this 100 meter change in height, and the horizontal distance over which that change in height occurs is 60 millimeters, which if we multiply it by our scale factor of our map means 90 meters in real life. So we can draw a triangle which shows this geometry. We've got 100 meters change between these 2 points, and that occurs over 90 meters. So the dip of our contact between the shale and the marl can be calculated as being the inverse tangent of the opposite divided by the adjacent, or in our case 100 divided by 90, which gives us a dip amount of 48 degrees. Now you can see from the map on the other side of the fold hinge, on the other limb, those structural contours are as equally spaced. They're kind of the mirror image of the structural contours we've just used. So we know just from that pattern of the structural contours that the dip of that limb, of the other limb on the other side of the hinge, must also be 48, albeit in the opposite direction, or in the synform direction. So therefore the interlim angle for our fold, if we were to take a slice perpendicular to the hinge, then we'd see that that interlim angle can be calculated as 180, all of the degrees in a triangle, minus the dip of the two limbs to give us an interlim angle of 84 degrees. Now, like I said, this is a fold which has a plunge. So its hinge is dipping. And again, just like we do for a plane, we can calculate the dip of the hinge by using simple trigonometry between 2 points where we know the height. And we've defined our fold hinge by looking at where we get this point of inflection for the structural contours. So these 2 points here, this is at 210. This is a point of inflection of our contact between the shale and the marl. And here that same point is at 100 meters elevation. The horizontal distance between which that height change happens is 88 millimeters on our map, which equals 132 meters in real life. So drawing a simple triangle to show that relationship, we can calculate the dip of the fold hinge by using the inverse tangent of the opposite over adjacent, which in our case is 100 divided by 132. So our dip of our fold hinge, our plunge amount of our fold hinge, is 37 degrees. So that's the plunge amount, or just the plunge. But then the plunge direction is measured just like any other direction as a compass bearing clockwise from north, and it's parallel to the hinge line or the axial trace in the direction of high to low. So if we're at high here, we're at 200, and we're at 100 down here, then the plunge direction must be in this must be going in this orientation. So we can line up a north arrow with our fold hinge, with our fold axial trace, and then we can count clockwise around from north in the direction of plunge, and that tells us that the plunge direction is at 246. Now the tricky question of the lab asks you to calculate the true thickness of the shale bed at location A. And in truth, you could calculate the thickness for anywhere along that shale bed, and it would give you the same result. We can see that because the structural contours don't change, so there isn't any variation in thickness. Now, we've got the height of one of the contacts of the shale, but there's another contact for the shale, isn't there? We've got the top of the shale at the moment, but what we should get is the bottom of the shale. Okay, so what we should then do is find all of the points where we find that other contact between the shale and the sandstone. We've got the contact between the shale and the marl. Those are currently highlighted in red. But what we need to do is get the other contact between the shale and the sandstone. So I found all of the points where I know the height of that other contact, and I've marked them on with crosses. And then by joining these points together, I can build structural contours for that other contact. Okay, so in red now I've got the upper contact between the marl and the shale, and in blue I've got the lower contact between the shale and the sandstone. Then what I can do is compare the horizontal distance between the same height structural contours for the top contact and the bottom contact, and that will allow me to calculate thickness. So let's just take a point near A, where I've got the top contact and the bottom contact, and I'm going to measure perpendicular to the structural contours that horizontal distance. So when I do that, that horizontal distance comes out as 9 millimeters, which when I multiply that 9 millimeters by 1.5, our map scale, it tells me that the distance, the horizontal distance between the top and bottom contact between those 2 points is 13.5 meters in real life. Okay, so I can kind of take a little sketch to show what I've done so far. I've got the bottom contact that's between the shale and the sandstone highlighted in blue here. I've got the top contact between the shale and the marl highlighted in red here. And for the same height for 150 meters, where they're both equal to 150 meters, the distance, the horizontal distance between them is going to be 13.5 meters. So what I'm interested in now, looking at my sketch, is the true thickness, the perpendicular thickness between the top and the bottom contact. I don't want the vertical thickness or the horizontal thickness. I want the true thickness, which you measure perpendicular to the contacts. So what I can do is maybe move this true thickness line to make myself a right angle triangle, and then I can use myself some simple trigonometry. I can show that the true thickness of my bed is equal to the sine of the dip, which I've already calculated, multiplied by the hypotenuse, and that gives us the opposite side, the true thickness, as equal to 10 meters. Now that question is slightly tricky, and it'll take a bit of time to sink in, but have a go at drawing those structural contours and have a go at working out that true thickness by using structural contours. It will click, I'm sure of it, and refresh yourself with this video as much as you need. Okay, I'll see you in our next lab, where we'll go to Newport to see some folded rocks on a real geological map. Okay, thanks guys, you have a good one.